Hi everybody, this is Mrs. Marsh, and today we're going to talk about optimization problems. So, an optimization problem in calculus is where we're finding the largest or smallest value of some function. So we're maximizing or minimizing some function subject to a certain constraint. And we're going to follow this process in which we have a primary equation and a secondary equation. And then we're solving the secondary equation, finding the derivative of the primary equation, and then possibly solving for another variable. So let's go through this process with an example. Example 1, the product of two positive numbers is 192 and the sum is a minimum. So first, we're starting off with writing the primary equation. This is the equation you're going to make as large or as small as possible. So looking at this problem, what do we want to minimize? We have that we want a minimum. We want to minimize the sum. So this is going to be our primary equation. We have two positive numbers. Now I can call these two positive numbers anything. I'm just assigning variables to each, so I'm going to call them x and y. I know the product is 192 and I want the sum to be a minimum. So I can write an equation for the sum of these numbers by x plus y is equal to. Now for our primary equation, this is just equal to some value. So the sum that we want to minimize is just equal to something. I'll just call that a capital S for sum. So we've written the primary equation. Now let's write the secondary equation. So the secondary equation is the equation that relates the unknowns. In this case, this is our constraint, and we're given that the product of two positive numbers is 192. So this is our constraint. And the product means multiplication, so I can say x times y is equal to 192. So we've got our secondary equation with our constraint. We've got our primary equation that tells us what we want to maximize or minimize. Okay, step 2 is done. Step 3, we're solving for the secondary equation for one known and then using that to eliminate one of the variables in the primary equation. So we're solving this secondary equation. This should actually be one unknown. I'll fix that. We can also call that a variable. Okay, so we're solving the secondary equation for one of the variables. Now, it doesn't really matter which. I could call x 192 divided by y, or I could call y 192 divided by x. It truly doesn't matter. So let's just divide both sides by y to get that x is equal to 192 divided by y. So we're going to use this to eliminate one of the variables in the primary equation. All I'm doing is I'm plugging in 192 over y in for x. So let's do that substitution and we get 192 over y plus y is equal to s. All right, we've successfully eliminated one of the variables in the primary equation. Now we're going to find the derivative of the primary equation, set it equal to 0, and solve for the missing variable. Now we want to find the derivative of s. So if I want to find s prime, I can find that derivative now that I only have one variable. I only have this s. This sum is a function of y. Now I can just take the derivative with respect to y. So I can essentially find that derivative normally. Now let's talk about the 192 over y. We have something like 192 over y. We can also write this. I know that an exponent of 1 in the denominator makes this a negative 1 in the numerator. So I can call this 192 y to the power of negative 1. And in this form, I like to do this so that I can use the power rule rather than the quotient rule. So the derivative of 192 y to the power of negative 1, using that power rule, we're multiplying this negative 1 by our coefficient of 192 to get negative 192, then we are keeping the y, keeping our variable, and subtracting 1 from that power. Well, if this is negative 192, y to the power of negative 2, then I can call this negative 192 over y squared with the y in that denominator. And so I know this derivative is going to be negative 192 over y squared plus, what's the derivative of y? Well, that's just 1. So we've taken the derivative. We've taken the derivative. Now we need to set the derivative equal to 0 and solve for the missing variable. So let's set this equal to 0. So 0 is equal to negative 192 over y squared plus 1. Okay, now we're solving. So let's bring this 1 to the other side. We get a negative 1 is equal to negative 192 over y squared. I know this y squared is in the denominator, so to get this out of the denominator, I'm going to multiply both sides by y squared. And I get negative y squared is equal to negative 192, which means by dividing or multiplying both sides by negative 1, if y squared is equal to a positive 192, then that means y is equal to the square root of 192. All right, so I've got my y. Now, depending on the question, we may need to solve for the other variable. So let's solve for the other variable. We know what y is. And now let's solve for x. We have this equation. The secondary equation will tell us what x is. So we will now plug this back into the secondary equation, and then we get that x is equal to 192 divided by the square root of 192. Now, while this might look just a little bit strange, we know that if we take, let's say, x, and divide it by the square root of x, because we've got the same base here, even though this isn't a variable, this is really like x to the power of 1 divided by x to the power of 1/2. And when we divide like bases, we subtract the exponents, and we're just left with x to the power of positive 1/2, which we know is the square root of x, which brings us to the conclusion that x is equal to just the square root of 192. And we just want these two positive numbers. So we have y and x are equal to the square root of 192. So to see what we're actually doing, kind of stepping away from this process that we've developed, is we are finding some equation that connects these two variables. So by doing that, by using this secondary equation that the product of these numbers is 192, we found the sum that we're trying to minimize with respect to one variable. So this is our equation, and we want to find the minimum of this. Let's see what the graph of this might look like. Just to make this a little bit easier on ourselves, I'm going to call this sy, and I'm going to call these two variables x, because we just want to know the minimum. All right, and looking at our graph of this, I love Desmos for graphing. Sometimes it's just a little bit easier. We get a function that looks like this. Now what we want is we want to minimize this function because these two numbers are positive. And so we have a graph in this shape. So what we're trying to do is we're trying to minimize something that looks like this. And how do I minimize this? Well, I know that at the lowest point of this graph, which is right here, this function has a tangent line with a slope of 0. I know at the minimum, f prime of x is equal to 0, and that's why we found the derivative and set the derivative equal to 0, to find the minimum. This same kind of deal works with the maximum too, because we know if we want to maximize this function, we know at that maximum point, then we can find a tangent line that's horizontal, which means that the slope, which is the derivative, is equal to 0. All right, let's do another problem. We have the second positive number is a reciprocal of the first, and the sum is a minimum. So first, let's write our primary and our secondary equations. All right, now our primary equation is the one that we want to maximize or minimize. We are given that the sum is a minimum. We're told that we're just dealing with two positive numbers here. So I'm going to call the primary equation x plus y is equal to s for the sum. For the secondary equation relates these two variables. So I have the second positive number is a reciprocal of the first. If we don't remember what reciprocal means, here's an example. Remember back into slope. We know that if we had a slope like 2/3 of a line, well, the perpendicular line was just the negative reciprocal. So the reciprocal of 2/3 is 3/2. We're really just flipping that fraction. If we wanted to take the reciprocal of a whole number like 7, we could really look at this as if it was 7/1, and the reciprocal would be 1/7. Now, while it might be pretty easy to find the reciprocal of a number, what if we don't know that number? So what if we've got something like x, and we want to find this reciprocal? Well, we know that when we divide a fraction, we're really multiplying by the reciprocal. So to get from 7 to 1/7, I would just take 1 and divide by 7. To get from 2/3 to 3/2, I would just take 1 and divide by 2/3. So that's how we get that the reciprocal of any number x is just 1/x. And so if our second positive number is a reciprocal of the first, then we can say that our second positive number y is just the reciprocal of x. So y is equal to 1 divided by x. All right, so we found the primary and the secondary equations. Our next step is to substitute one of these variables in the secondary equation into the primary equation so that now we have a function of one variable. So I'm just going to write the s in front, it doesn't matter, so that this sum is equal to x plus, well, my y is 1/x. All right, now I've got my primary equation in one variable. Our next step is to take the derivative because we want to maximize or minimize this primary equation. We want to see where that derivative is equal to 0. So the derivative, s prime, is equal to, I know the derivative of x is 1, and just like the logic in the last problem, I know the derivative of 1/x is just negative 1/x squared. I've found the derivative. I need to set that derivative equal to 0. So I'm solving the equation 0 equals 1 minus 1/x squared. I can add 1/x squared to both sides, so I get 1/x squared is equal to 1. I can multiply both sides by x squared to get that 1 is equal to x squared. All right, now the square root of x, because we're given that these are both positive numbers, x must just be equal to 1. So my first positive number is 1. I can plug this back into the secondary equation, y equals 1/x, to find y. So because x is 1, y is 1/1, which is just 1. And so I have x is 1 and y is 1. So the first two numbers are just 1. And does this make sense? I want my second positive number to be a reciprocal of the first because we know that 1 over 1 is just 1, so 1 is a reciprocal of 1. I want their sum to be a minimum. And we can see how any two numbers larger than this, say we have x of 2, a y of 1/2, well 2 plus 1/2, which is 2.5, is larger than 1 plus 1, which is 2. If we had 3 and 1/3, well the sum would be 3 1/3, and we can see how that would just continue to increase. And so when you solve these problems, just make sure that you think about these logically. Think about how we can describe this situation with variables, and then look at your answer and say, does this make sense? So let's do another problem. The perimeter of a rectangle is 50 feet and the area is a maximum. We want to find the area. Okay, so we're given that the perimeter of a rectangle is 50 feet, so I'm just going to draw out a rectangle. Well, I know with a rectangle, the length on one side is the same as the length on the other, and I know the width on one side is the same as the width of the other. So this is our rectangle. We want to find a primary and a secondary equation. So if the perimeter is 50 feet and the area is a maximum, well, we know the area of a rectangle is just length times width. So I'm going to write that as my primary. Area is just length times width. Now how can we describe the perimeter being 50 feet? Well, we know the perimeter is just the sum of all of the sides. So I can say that the length plus the length, which is 2 times the length, plus the width, which is 2 times the width, is equal to 50 feet. So I've got my primary and my secondary equation. Now we are solving the secondary equation for one of the variables, and it does not matter which. Let's just solve for length. By subtracting 2w from both sides, we get that 2 times the length is equal to 50 minus 2w. All right, we can divide everything by 2 to find that the length is equal to, well, 50 divided by 2 is 25. 2w divided by 2 is just a negative w. So we've got that the length is equal to 25 minus the width. So let's plug this into the primary equation. We get A is equal to, instead of L, we'll write 25 minus W times the width. Now I want to take the derivative of this. If I take the derivative of this as is, I'm going to need to use the product rule because I've got the product of 25 minus W and W. But I don't have to do that. If I just distribute this W first, let's see what happens. I get A is equal to 25W minus W squared. Doesn't that make our lives a whole lot easier? Because now we can just use the power rule for each of these terms. And we can get that A prime, the derivative of this area function, is equal to 25 minus 2W, just taking that derivative. Because we want to maximize this, we're setting it equal to 0. We're setting that derivative equal to 0. And solving for W, by adding 2W to both sides, we get 2W equals 25, and by dividing by 2, we get that W is equal to 25 over 2, which is 12.5. Remembering that everything is in feet, let's just add that unit. So we get that the width is equal to 12.5 feet. All right, we need to find the length. We can use the secondary equation. Length is equal to 25 minus 12.5. And so the length is just also equal to 12.5 feet. Okay, we have a width and length. Here's where that last step comes in, where we look back at the problem and maybe have to do another step to find out what we're asked. We're asked to find the area. Well, we found the width and the length. So now to find the area, we know that we just multiply these two. So area is equal to the width times the length, which is equal to 12.5 feet, times 12.5 feet. And so this is equal to 156.25. Because our units are feet times feet, we have feet squared. So this is our final answer, 156.25 feet squared. This width and this length, in this case, were really just intermediate steps. Okay, let's do another example problem. A farmer wants to separate his male and female cows in a rectangular field that has an area of 12,000 feet squared. We want to find the maximum amount of fence needed, and this time we're told to round to the nearest hundredth. So just make sure that if we're not told to round, then we want things in form of a simplified fraction or possibly pi. Okay. So a farmer wants to separate his male and female cows in a rectangular field. Let's start there. So we've got this rectangular field. This rectangular field has an area of 12,000 feet squared. We want to separate the male and female cows. Now, if I were to add a piece of fence lengthwise or widthwise, so I'm going to add a piece of fence here or here. Well, I know that this width, at least from how I drew the picture, is wider than this length, right? So I'm just saying, okay, I want to separate with some length of fence. And what I'm going to do is I'm going to label all of these sides because I know that this has an area of 12,000 feet. The entire field has an area of 12,000 feet. And so I need to categorize this in terms of certain lengths and certain widths. Now, I'll call this large piece of fence a width. I know because this is a rectangular field, this large piece of fence is also considered a width. And then I've got these shorter pieces of fence that I can call lengths. Okay, so I've got 3 lengths and 2 widths. Okay, so let's find our primary and our secondary equations. So I'm given that this is a rectangular field with an area of 12,000 feet squared. Let's start there. Area, which is equal to, instead of calling this area, let's just call this 12,000 feet squared, is equal to the length times the width. In this case, my area is the constraint, so that'll be the secondary equation. I want to find the minimum amount of fence needed. So amount of fence looks a whole lot like perimeter. So my perimeter is made of these 3 lengths plus these 2 widths. All right, so I've got my primary equation because I want to minimize the amount of fence needed. I've got my secondary equation, which is that the area total is equal to 12,000 feet squared. All right, let's solve this secondary equation for one of the variables so that I can maximize or minimize this primary equation. So it does not matter which we use. Let's just divide both sides by, let's say, the width, and we get that 12,000 divided by the length is equal to the width. So let's plug this into our primary equation. We get P is equal to 3L plus 2 times 12,000 divided by L. Just like in the last problem, we're going to want to simplify this before taking the derivative. It's just a whole lot easier that way. So we get that the primary equation is 3L plus, okay, we get 2 times 12,000, so that's 24,000 divided by L. Next, because now we have an equation in one variable, we can just take the derivative of this primary equation. Derivative of 3L is just 3, and the derivative of 24,000 divided by L is a negative 24,000 divided by L squared. We're going to see this derivative a lot, so we kind of get used to this. And so now we're setting the derivative equal to 0, because remember, if we want to find the maximum or minimum value of an equation, we're finding where the derivative is equal to 0. So this derivative is equal to 0. When we set the equation 0 is equal to 3 minus 24,000 over L squared. Let's add this term to both sides and get 24,000 divided by L squared is equal to 3. We want to isolate this L squared. It's a problem in the denominator, so let's just multiply it by both sides so it can be in our numerator. So we've got 24,000 is equal to 3 times L squared. Next, we can divide by 3, and we get that L squared is equal to, this becomes 8,000. Taking the square root of this length, well, I know that length has to be positive, so we're discarding that negative value. We get that the length is equal to the square root of 8,000 feet. Now 8,000 isn't a perfect square. And so what I'm going to do is I'm going to make sure this is the last step of my problem before rounding, because whenever we have any kind of problems in general, in math, science, anything, we want to try to not round until the end. Because if I round intermediate steps, then it forces the error in my final answer to be even greater. So we just want to be careful of that. And so I've got that the length is the square root of 8,000 feet. I want to find the minimum amount of fence needed. So because this isn't my last step, I'm going to leave this as is, so I can get a more accurate width. And so my width is equal to 12,000 divided by the square root of 8,000 feet. So I've got my length and width. The amount of fence, we said, is just this perimeter. So that's the amount of fence needed. And so our final step of this problem is the amount of fence is going to be 3 times that length plus 2 times this width. And so doing just a quick calculation here, we get that the amount of fence needed is about, rounded to the nearest hundredth, 536.66 feet squared. So this is our total amount of fence needed. Okay, let's do one more practice problem with this. And I know that our process can get just a little bit confusing, but if we remember how to set up the primary and secondary equations, we want to find the maximum or minimum of this primary equation by setting the derivative equal to 0. Then we just need to look at this problem and use a little bit of our logical reasoning to actually answer this question. All right, one more problem. We've got a sheet of cardboard that has dimensions 28 by 20 centimeters. Squares with length x will be cut out of each of the four corners so that the sides can be folded up to create an open top box. We want to find the value of x that will maximize the volume of the box, rounding to the nearest hundredth. So I've got a sheet of cardboard that is 28 by 20 centimeters. Let's do a rough sketch of this. Okay, this side looks a little longer, so I'll call this 28 centimeters, and I'll call this width 20 centimeters. We are told that squares with length x will be cut out of each of the four corners so that our sides can be folded up to create an open top box. So I'm cutting squares of length and width x out of all four corners. Let's see, so we're trying to make these kind of the same width and length here. Okay, and we've got length and width x of each of these boxes. So these are all going to have a length and a width x. Okay, these are going to ultimately be folded up to create an open top box. So let's see what this might look like. When I fold these up, when I cut out these boxes of length x by x, I get something that looks like this. Okay. Okay, open top box like this. I want to find the value of x that will maximize the volume of a box. I want to round to the nearest hundredth. So I know that my primary equation is going to be the one that maximizes or minimizes a value. So primary equation, I want to maximize the volume. So what's volume? Volume is just length times the width times the height of a box, right? Now, my secondary equation might be a little bit more complicated. Because we're trying to describe this situation. So how do we describe that the volume of a box is going to be a piece of cardboard 20 by 28 minus all of these boxes, these squares with length and width x? So here's what I'm going to say. I'm going to try to go from here to here and just write the length, width, and height of this box in terms of x. Okay, so if I know that the width of this cardboard is 20 centimeters, and I know that I'm subtracting these boxes of length and width x, then can I say that this new box, this portion right here, which is going to be the width of this box, this portion of the box is really 20 centimeters minus x, which is 20 centimeters minus 2x. Do we see that? Because if we cut out these boxes of length and width x, we're really taking the 20 centimeters, subtracting 2 times the width of this box x, because this is going to become the width of this box. If we can kind of imagine that we're folding these four sides of this box up. So this is the length and the width of this box. Now for this other width or length, whatever we want to call it, for this other dimension over here, we're looking at this length. So we're taking 28 centimeters. And again, we're subtracting this length x and this length x. And so this region in here, we can say is 28 minus 2x. All right, what about this height? Well, what's the height of the box going to be? Height of the box. Well, again, if we're folding up these four corners, these four rectangles we're folding up, then isn't the height of the box just going to be this x? So our height of the box is just going to be x. And so this is going to form our secondary equations in this case. And this is why we say that in that last step of your instructions, we say secondary equations, not always necessary. Well, in this case, what I'm going to do is I'm just going to rewrite this primary equation in terms of x. So our secondary equations, because they're just that the height is equal to x, and let's call this the length is equal to 28 minus 2x, and the width is equal to 20 minus 2x. Then I can just plug these into this primary equation because I know that's my next step, is to plug the values of the secondary equation into the primary equation because I only want this to be a function of one variable. If I tried to take the derivative and I've got three different variables, we can see that that would be quite a pain. And so I can rewrite this volume as the length, which is 28 minus 2x, times the width, which is 20 minus 2x, times the height, which is x. So we did these first few steps. So now our goal is going to be to take the derivative of this primary equation, set it equal to 0. But before I take this derivative, because I have three different things multiplied together, I'm just going to do this multiplication. I do not want to take the derivative like this. And so let's just rewrite the volume. So the volume is going to be, I'll start off by, I'll work with this x at the end, and then I'll just FOIL these. 28 times 20 is going to be 560. So I've got 560 times the outside, which is negative 56x, the inside, which is negative 40x, and the last two terms, which give us a positive 4x squared. And then distributing this x and writing these in order, I get 4x cubed minus 96x squared plus 560x. All right. Now, because I've just got three different terms that I can use the power rule with, let's take that derivative. We get that the derivative of the volume, just using the power rule, is going to be 12x squared minus 192x plus 560. Now the question is, I want to set this equal to 0. I've got a quadratic equation. Now, if I can factor this, I will absolutely factor this. The question is, can I factor this? So first of all, can I factor out a 12? And I can see that when I divide 192 by 12, I get 16. Great. When I divide 560 by 12, I get 46 2/3. So I can't take a 12 out. So I can try some other value. However, because these coefficients are so large, this is still going to be kind of a pain to factor. And so now let's just use the quadratic formula. So using the quadratic formula, we've got an a of 12. So using the quadratic formula, we've got an a of 12, a b of negative 192, and a c of 560. And so these zeros are going to come from negative b. So 192 plus or minus the square root of b squared minus 4ac all over 2a. Just doing this in the calculator, we get that this discriminant, 192 squared, minus 4 times 12 times 560 is going to be the square root of 9944, which is about 99.91. So we're going to have x is equal to 192 plus that divided by 24. It's going to be 12.16. And our units are in feet. I'm sorry, centimeters. Or if we take 192 and subtract that answer, dividing it by 24, we get 3.84. All right. Now the question is, which is the correct answer? So this is where we have to look back at what type of problem this is. If we have a box that is 20 by 28 centimeters, so when we check for the validity of each of these answers, we've got a box that is 20 by 28 centimeters. From the length and the width, we are subtracting boxes of 12.16 by 12.16 centimeters. Well, that's going to be more than half of this width. If I take away a box that's over 12 centimeters by 12 centimeters, I'm taking this box of length x and width x, and I'm also trying to take away this other box of width x and length x. Because 12.16 is more than half of the length of this, I can determine that 12.16 centimeters would make no sense. We would have a negative amount of cardboard. And so that is how I can conclude that 3.84 centimeters is going to be the length and width of these boxes, x by x. So sometimes it just takes looking back at this problem and just analyzing what we're really talking about to determine which length or width is reasonable. And so this concludes our lesson on optimization problems.